All right. Hi, I'm Sam Kocsis with the Amphenol Corporation.
Hi, Vasanta Madduri with Broadcom. So good afternoon, everyone. I think we are one of the last presentations, so thanks for attending. Today, basically, our title is Beyond UBB Scaling Out with OAI Expansion Module. So our focus today, I think, is going to be on the expansion module, as it says. We will cover all aspects and considerations of it. Basically, the expansion module allows for scale out. So I think you heard in the previous talk from Meta on Grand Teton how there are challenges for SI at Gen 5. So we have similar, charter within the OAI work stream that there are going to be challenges at 100 gig also to implement this. And we took on in the previous two OCPs simulations, simulation, validation, and at this OCP, we're down to demonstrating. So that's what we're going to, Sam and I are going to cover today. Again, I think there was a talk earlier with Song and Ahmed, basically talking about the OAI specs and OAI system blocks. So just very quickly, the components here, which in relation to the expansion module, which are important, are for signal integrity, which are important, are the OAM module, which is the open accelerator module, and the UBB tray, which also has signal integrity implications, and I think the previous presentation talked about it. And our focus again is the expansion module, which connects the high-speed SerDes on these OAM modules through connectors onto the external connectors, which are the 4 OSFP modules on each one of these expansion modules. So I think Song and Ahmed gave an update where the specs are. And again, we want to stress that for expansion module, what is critical in terms of this signal integrity study? The fact that the OAM modules have 8, the OAM universal baseboard has actually 8 OAM modules is significant, because when you have 8 of these modules located, the longest trace length becomes very important for signal integrity. The second is that the OCP accelerator, that was for the UBB. The OCP accelerator OAM module, it defines the mezzanine connector. Right now it's defined with the Molex connector in there. And then the expansion module itself is defined such that basically you can connect multiple OAI systems, and that's critical. Or you can also connect to, that's between different racks, or you can also connect to an external Ethernet switch. So that's where the expansion module comes in. The expansion module, again, as it was mentioned in the previous talk, is the latest addition to this work stream. So we recommend everyone to go out and look at this expansion module spec. But briefly, there is a power defined for this, which is around 400 watts. When scaling out, which is the focus of this topic, that is, I think, that allocation is more than sufficient. In fact, when scaling out with retimers, it's much lower. There are solutions out there. Basically, one of the vendors has an 8-lane solution at 100 gig. So in that case, with 4 OSFP modules, you'd be using 4 retimers on this expansion module. And in case of Broadcom's product, we have more integration. We have a 16-lane device. But the reason the 400 watt is spec is because the expansion modes spec is envisioned to have more use cases beyond scale out. So that's why the power is defined as that. And then the links that we are talking about are at 100 gig, which is the speed. So I talked about the expansion module spec having the 8 OAM modules. So what this visual shows is the OAM, the longest channels, and for scale out. That's the focus right now. And the longest channel for scale out is what we try to emulate, because those are the challenges that we want to solve ahead of adoption. In fact, in terms of adoption, we know at least a couple of vendors who have already adopted some variation of this spec, and they are putting that out with the expansion modules in place. So as more and more the AI and ML use cases arise, and larger and larger systems are built, the scale-out challenges need to be addressed. So to do this study and also to do the validation, real-world validation, the channel itself for the scale-out was divided into 2 portions, from the OAM module to the expansion module, and then the expansion module to the expansion module. So that's how it has been divided in our study. Also, I just want to point out that there can be other topologies which can exist. Expansion module to expansion module, we've used DAC cables, but there can be active electrical cables and optical links, and there's several solutions available from our partners, Amphenol, Molex, with retimers from Broadcom and several other vendors. Okay. So why is signal integrity critical? Like I said, Grant Teton presentation talked about these points. So it's exactly the same points for the 112 gig, right? So if you're having this high speed, because for the AI ML systems, you need the high throughput, basically, you are obviously running into crosstalk. So you need to lower the crosstalk. Lower crosstalk means longer physical reach, which is needed for when you're connecting these systems through cables. Fewer impedance discontinuities is also very important, because the I margin, it means greater I margin and better SNR. Then there is also, you can control all of that through thoughtful pin map definition to reduce bottlenecks. And that's very critical, and a lot of attention was paid to that. And that's what Sam will start talking about.
Thanks, Vasanta. So the OAI expansion module being the last part of the OAI ecosystem, we had to live within some of the framework that the UBB and OAM had established. So just as sort of a precursor, this kind of shows the footprint of the OAM module and where the TX and RX pairs are laid out in relation to the device itself. This is the links that we need to match up on the expansion module for both the retimer and switch applications. On the OAM, there's some space between the TX and RX pairs that provide adequate separation, reducing crosstalk. On the expansion module, we don't have quite that luxury. So connector 1 and connector 2 here on the screen are shown not as they're configured in the actual expansion module, but this hopefully helps you provide a little bit of visibility into how the TX and RX are separated. So it's separated vertically within the pin map. And this helps enable separating on separate layers, TX and RX routing, as you go through the UBB footprint transitioning to the expansion module. This is a nice way to provide isolation where we don't have the physical space to provide the isolation itself. And really, if you're doing the retimer application, you would only need one of these connectors. And the spec details both implementations a bit further. So if you are interested, we encourage you to obviously pick up the spec and go through the preferred implementation. One of the key things with respect to the pin map is how that fits into the stack up. So in addition to the backplane style connector that's used to transmit the high-speed lanes, there's a Gen Z 2C connector, and that Gen Z 2C connector has a defined thickness for the PCB. So that set the limit for our PCB thickness and the number of layers that we'd be able to get out of this module. We needed to have at least 4 high-speed routing layers. This helps us maintain the isolation between TX and RX. We also needed adequate power to support the 400 watts, but obviously for some applications we can do much lower than that. In general, we would certainly recommend ultra-low loss type of material, and we have the flexibility in the spec. We've offered recommendations for both 85 and 90 ohm impedance varieties. One of the interesting things we did with the stack up here, because it's a backplane style connector, is we put the high-speed routing in the center of the board and the power on the outside. This helps enable back drilling for all of the high-speed layers, which will give you the optimal signal integrity path. So the next few slides, I just pick out a few of the key pictures that are in the document. These show how the network topology from the OAM to the expansion modules is achieved. You can see on the left, it's more of the retimer topology, and on the right, it's the switch topology. When you look at how that permutes to a expansion module layout, it looks something like this. On the left, with the retimer topology, you only need the one backplane style connector. You could have 4 retimers as shown here, or some technologies will combine those into 2 devices or even 1 device. On the right, you have a switch implementation where you would absolutely need the additional backplane style connector. And then over to the left, there's a picture of the 2C implementation, which is used for power and the control plane. So just to highlight what some of those features that we would support with that is, this is the 2C connector for the control plane. This is where we get our management control interface. A lot of our communication protocols would go through here. And most importantly, the access to the 54-volt power input. Mechanically, there's been a lot of thought put into this as well. I would consider this sort of a base specification plus. It's not a full reference design, but certainly provides the thoughtful inputs to have implementers pick this up and be very close to completing a reference design that could come to market. So these are the dimensions of the expansion module. It's very similar in size to an OCP NIC, with the attachment mechanism very similar to maybe a PCIe add-in card. And recognizing that this is absolutely required to have the utmost signal integrity, it's not a card edge solution doing the high speeds transmission. It's a more backplane style connector. So as Vasanta mentioned, we had a couple of presentations, contributions at OCP events in the past. We did a lot of simulation work and budgeting these 2 topologies. We've certainly based this off of the Ethernet specification in terms of ball-to-ball loss requirements, allocating a portion for the OAM, a portion for the expansion module, and a portion for the UBB. Certainly specific implementation details may vary if your device is more capable or if your interconnect requirements are a little bit different. Different PCB materials will also lead to varied results. But what we wanted to do was come up with a way to demonstrate this and demonstrate technical feasibility with real parts. So in the Experience Center this week, we've had this display, and we've had a lot of great conversation, a lot of good traffic through the Experience Center. On the left is sort of a mock-up picture, a mock-up of what the product would look like. And then on the right, we have all of the actual components that would go into that system working and providing verification of the signal paths. We'd like to thank Multilane for their support with the ISI board, standing in as a proxy for the trace on the UBB. And then Molex and Amphenol provided the interconnect solutions to help complete the channel with the Broadcom device on either side. So we did this for both the expansion module to expansion module links with an OSFP DAC cable, and we did this for the OAM to expansion module links with the Multilane ISI board. One of the things we're often asked is just about developing this. There's obviously a physical reach implementation aspect to it, but also a crosstalk component. And what we really wanted to do in evaluating these links is look at practical topologies and not look at something that may be too idealistic, since we are using test fixtures. So we chose victims and aggressors based on practical implementations from the pin maps, as well as what we would have access to in each of the test fixtures. So for example, on the expansion module with the backplane connector, we take the victim, as I circled in green. We don't have access to all of the possible aggressors, but we know through simulation and measurement which ones would have the most contribution for crosstalk. So we focused on measuring and evaluating these links with those pairs, providing the noise through the link demonstration. Similarly, on the OSFP side, depending on the pair that you choose, you may have more far-end crosstalk than near-end crosstalk. We've tried to best approximate what we could get access to with the equipment that we had available to us. So the results are pretty promising. This is, again, both topologies, expansion module to expansion module. We looked at the results without any crosstalk. The insertion loss shown here is measured die to die, as opposed to ball in the previous topology. This is what we had access to with the device. It gave us great visibility in terms of the end-to-end loss. And we can compare the two topologies together. We can look at the effects of crosstalk. It's pretty clear that the expansion module to OAM links have significantly less crosstalk. We're able to go a little bit further. But in both cases, we're able to achieve very impressive BER, much better than what we see as a requirement for the Ethernet spec. And we feel like this gives a pretty strong vote of confidence to implementers looking to choose this solution. So for our call to action, I think it's been mentioned a couple of times that the OAI 2.0 specs are available on the wiki page. They're publicly available. I encourage you to take a look at those. As Vasanta mentioned, there are some OAI adjacent deployments that we see in early production right now. And we really, our call to action is to bring more of these types of solutions to the field, to the market, and then feedback to the OCP community as we try to figure out next steps, what worked, what we need to do going forward, whether it's thermally, signal integrity-wise, mechanically. And so join the OAI subgroup, contribute on the mailing list, and check the server project for updates. I think with that, we may have time for a couple of questions if there are any.
All right. If there are no questions, thank you, Sam. Thank you, Vasanta.
Thank you.